Okay. So this session, this annual meeting, we're glad to have Chia, our old friend, to give us a nice talk. Light resonances from a hidden color age group. Let's welcome Chia.
Hello? Okay. I would like to thank the organizers for the invitation. And Kim told me to talk about some most recent work. So I choose the topic is based on work still ongoing, so not finished yet, with my former student, is in our audience, not the other famous professor, but hopefully become famous in the future. And Daniel Savioni, former postdoc, and Christopher, current postdoc at Davis. Okay, you know that the hierarchical color or standard model has been the main driven force in new physics search. If the hierarchy problem is solved by symmetry principle, either by supersymmetry or global symmetry, then we expect new particles to be there and coupled to Higgs, so that they can cancel the quadratic contribution from the standard model particles to the Higgs potential. Now, because the top quark has the biggest coupling to the Higgs, we expect there should be a the top partner, which cancels the top loop, should be very close to the weak scale. But of course, such top partners has been extensive searched at the colliders. Now at the LHC, we have a very strong limit now, either a scalar top partner from supersymmetry or fermionic top partner from global symmetry. The bounds are basically above TeV with some small holes below it, but now they look like the situation is so the situation makes people worried about this naturalness explanation. However, of course, these searches basically assume that these top partners carry standard model color gauge group. Therefore, they have very large production cross-sections. So one way out is to consider models such that, in fact, these top partners do not carry standard model color gauge quantum numbers, so that their production rate is much smaller, and therefore can still be light enough to address the naturalness problem. The first of such model was the twin Higgs model proposed in 2000 by Charco, Go, and Harnick. Now, in recent years, because of the strong limit, people are getting more interested in this type of models, and many different models are proposed in this category. Now, these models can be basically divided into different categories based on the quantum numbers of the top partners. On this side, we can have the spins, either spin 0, like a supersymmetry, or spin 1/2, fermionic top partner. Then on the rows here, we have the standard scenario where the top partner carry all standard model charge, including color and electroweak charge. These are the traditional model, like supersymmetry or Lambo-Goldstone boson Higgs type of scenario. Now, in neutral naturalness models, these top partners do not carry color charge, but they can either they carry electric charge or they don't carry any standard model charge at all. So these are different type of models listed here. Before this year, there was a missing entry here, but this year there are two models appears which fill this entry, and one of this was a model proposed by us, and we will use this as an example for our studies. And now these models can also be viewed as provide some motivated targets for the general hidden valley type theories. Now, in principle, one can imagine there's a hidden sector which very interactive with our sector very weakly, and we may, but such a possibility is, well, the possibilities are too big. So in order to set some motivated target, I think these provide very good examples, and also hopefully their signatures are, experimental signatures are good representations of the whole hidden valley model. Now, in all these proposed models, there's a generic feature that even though these top honors do not carry standard model color charge, they are usually carry some hidden colors. They have to charge. The reason is that in order to address the hierarchy problem, there should be a cancellation between the top contribution and these top honor contribution. So their coupling to the Higgs should be related. But because they receive radiated corrections, at least the standard model top receive the radiated correction from the color gauge group. So in order to keep this relation, the top honors should carry a hidden color charge, and the coupling is related to the standard model color coupling. Because there is a hidden strongly impacting color gauge group, in general, we also expect downstate in the hidden sector formed by this hidden color force. Now, and the scale of this hidden color should be related to the standard model color. Now, typically, because the hidden sector usually is heavier, or if you only need the third generation cancellation of third generation, there are maybe fewer states than the standard model. So usually the coupling runs faster. In general, we expect this strong scale of hidden color is somewhat larger than the strong scale of the strong interaction. So typically, one can expect the strong scale to be on order 100 MeV, similar to the strong scale of the strong interaction, up to maybe tens of GeV. That's the roughly lagging scale for these type of models. Now, when we have this strong force, we can divide this case into two possibilities. Depends on whether there are light states which are transformed under the fundamental representation of the color gauge group. One case, because you only need to cancel the basis of the third generation, it's possible that you only need to introduce these heavy hidden color states. In this case, the hidden color string cannot break. Then these hidden color states are usually called quarks, or if they are scattered, they are called quarks. Now, this has been studied just for logical reasons, but they appear naturally in these neutral network models. And for example, appears in fraternal twin Higgs model, folded SUSY model, and so on. Now, this is their phenomenon has been extensively studied, and this is not my focus. We will discuss the other possibility that there are, in fact, light states which can break the hidden color string and form light hadrons. So this is the phenomenon we will be discussing in this case. Now, when we have this light state, we imagine their intrinsic mass is less than lambda of the hidden QCD. That means they are light. They are below 100 GeV. So if they carry electroweak charge, then they probably ruled out because they can already be found, should have been found experimentally. So we expect this light state should be basic standard model singlet. However, if this they belong to the sector which address the hierarchy problem, we expect there are heavy states which couple to the electroweak gauge group, which couple to the Higgs. So in principle, these light singlet state can mix with heavy state, which carries standard model electric charge by coupling to the Higgs. So once Higgs get web, they can mix these states. So through these mixings, this light mass eigenstate can pick up some small couplings to the standard model Z and Higgs bosons. Therefore, they can appear in the real Z and Higgs exotic case. This will provide a good way to look for them. So to make the whole thing concrete, we will discuss this in a concrete model. This is a model, the triple top model proposed earlier by us. And in fact, we will not discuss that particular model we talked about. In fact, it's a variant of this model, a very simple variant. Let me just quickly introduce this model and give a brief explanation. Actually, how this model addresses the naturalness problem is not very important for this study, for completeness. So let me just give you a description. The model is based on supersymmetric extension of the standard model. In addition to supersymmetry, we also extend the SU3 gauge group to 3 copies. SU3, we call it ABC, 3 copies. SU3A represent the standard model color gauge group. Now here we have the usual Yukawa coupling. They belong to the standard model sector in the superpotential. Now in the other sector, we also have this new quartz, but carry hidden color charge. They also couple to the Higgs in a similar way. These Yukawa coupling are related by Z3 symmetry, so that relay their Yukawa coupling, so that they can cancel the quadratic divergence. The difference is that instead of chiral top quartz, now the hidden sector, these fermions are vector-like, so that they can receive a supersymmetric vector-like mass. We call them the double mass M, capital M, and single mass omega. And we will take the value capital M to be in the range of a few TeV, where this omega is much smaller. Now in the original model, these two are switched, but now we switch their role in this particular case. Now in addition to the symmetric superpotential, we also have the soft Susy breaking masses. Now here is the leading contribution to the soft Susy breaking mass. Take this particular form. We get some soft breaking mass to the usual top score of order m delta square. This is also large, of order few TeV, so that raise the usual stuff above the experimental bound. Then, in addition to that, then the hidden sector fermions receive a negative soft breaking masses. Such that although, well, these Qs, they have a large vector-like mass, but they also receive a negative contribution to the soft mass. So actually the scalar component of that mass is reduced down to a few hundred GeV. Their mass scale is represented by this delta. So there is some cancellation between these two big numbers. So this requires the soft breaking mass to be close to this capital M. And it also needs this special relation that the positive soft mass, the magnitude of this positive soft mass and the magnitude of the negative soft mass are equal. I mean, at least to a good approximation. Now, so it's basically, if you calculate now the loop correction to the Higgs potential, you find the standard model top quark contribution is cancelled by the scalar of this QB delta and QC delta. They are cut off by those at a few hundred GeV instead of the usual stuff and a few GeV. This is the way we can address this naturalness problem. So this is basically the summary of the some basic point of this model. The top Yukawa coupling pattern is like a Z3 symmetry, which which also relates the SU3 gauge group. And it's softly broken to Z2 by mass turn. Now we need these two sectors because we know that there are left-handed cups walk and right-handed one, so we need two of them to cancel the divergence. So here they are placed by the row of QB and QB.
What is this so good? I mean, you introduced Susie already.
Yes.
You have this seemingly a fine tuning with these two mass scales.
Yes.
So why don't you just, I mean, you could have a 2 TeV stock and looks like it's...
Well, the tuning can be reduced a little bit. Of course, the other thing is whether you can find the reason to expand the closed cross-union. In fact, that's let me just say this, that this model is natural from bottom point of view. If you go from bottom up, the divergence are canceled. But it does require some special relation. Not only the equality here, these two has to be equal and opposite. This requires model building, which we discussed in our original paper a little bit, but this is not important for our discussion here because we are really just care about the demand. So this is like a slope model, just really to produce the states that we want to study.
Do you need supersymmetry to get those states?
Huh?
Do you need supersymmetry to get the states you're interested in?
Actually, no. I think this type of thing can also happen in original twin Higgs model if you add some UV completion on the twin Higgs model. Not in the original spectrum, but you add some new state at the TeV scale to UV completion, it will also have something like this. Okay. Yeah, let me just say this model, in fact, it's not belong to the top honor in this case carry electric charge because they are electric doubled in this sense. So now, because hypercharge is weak, so actually there's a freedom, they don't affect the hierarchy problem too much. So there's a freedom to choose the hypercharge on these new fermions in the hidden sectors. In particular, we will choose these singlets to be these singlets have no hypercharge, and then these doublets carry hypercharge 1/2. Now these singlets are completely neutral under the standard model now. So their vector line mass can be very small without violating any experimental bound. We can make their mass to be lighter than the strong scale of the hidden sector. But however, they mix with the heavy state, which carry electric charge by their Higgs band because they couple to these guys, which they are heavy in the multi-TeV scale. So in fact, to find mass eigenstate, we need to diagonalize this 2x2 mass matrix. There's a right-hand mixing angle and a left-hand mixing angle. And typically in this model, we expect the right-hand mixing angle to be of order n top over this heavy state scale of a few TeV. So we expect this mixing angle to be of order maybe 0.1-ish. The left-hand mixing angle is further suppressed compared with the right-hand mixing angle by this additional factor m psi is the very light eigenstate of maybe G-ish. So this is 10 to the -3-ish. Now this mixing angle give us the coupling between these light fermions and the Z and the Higgs of the standard model. Actually, the Z coupling is suppressed by this right-hand mixing angle square, the order 10 to the -2. The Higgs coupling is suppressed by the left-hand mixing angle, maybe 10 to the -3 or even less. So up to this point now, you can basically forget about the model completely. So this model is basically just give you some motivated target for the size of these two mixing angles. And in principle, you can just start from here, say this light state cup with a small coupling to Z and Higgs, and then discuss their technology. But I think the purpose of the introduction model to give us some target value for how big this mixing can be. Now these mixings will govern the exotic Z and Higgs decay into these hidden fermions. And also they will also govern these light hadrons decay back into the standard model. So they are all related. Now, given this is expected number, we can estimate what's the branching fraction of the Z decay or Higgs decay into these hidden sector fermions. For a typical number like M2TB, the branching fraction of Z into this sector is about 10 to the minus 5, and Higgs into this is about 10 to the minus 4. But this one depends also on the strong scale of the hidden color. Now, these light fermions that are produced will hadronize and form light hadrons. In this particular model, this hidden sector has just one light flavor. For one light flavor, for one flavor to see the lightest meson from the hidden sector, I expect to be a pseudo-scalar, a vector. These two are probably close degenerate, and then the higher one is a scalar particle. Their mass is maybe expect to be about 3 times of the strong scale. Then, because these fermions are small coupling to Z and H, they all can decay back to the standard model particle through the Z and H couplings. And one can estimate their decay length of these particles. For the pseudo-scalar, if we pick some typical number, one finds it's still clumped, but close to be displaced. If this pseudo-scalar decay to BB bar is open. If it's lighter, lambda smaller, and this channel is closed, then we may expect this decay will be displaced. Have a microscopic decay length. Now, upsilon in general decay through Z is in general is expected to be prompt, but if you consider very small lambda or very large m, it's also possible to make it displaced. Now, the scalars can decay in 2 ways: either go back directly to the standard model through Higgs mixing, or it may be excited down to lower state, depending on their mass splitting. Typically, we found that the excitation is faster, and also the decay length is close, is in the borderline of being whether one can see the displacement or not. Now, the decay of the Z or Higgs into the hidden hadrons, how do they decay into these hidden hadrons? Now, depends on their mass. Their mass is controlled by this strong scale of the hidden color. If the lambda is big, say bigger than 10 GeV, then these hidden mesons can have a mass of like 30 GeV. Then basically, the Z and Higgs decay are dominated by two-body decay, so there's really no phase space to decay into more mesons. In this case, the Z decay, the leading decay is probably to a scalar and a pseudo-scalar. The decay to vector mesons may be suppressed by lambda because you need a chiral flip. So this is a general expectation. It's suppressed but non-negligible. Higgs maybe decay into a pair of identical mesons, and or if it's open, it may decay into three-body decay because these will be suppressed by lambda, but this does not. Now, if lambda is small and if these light mesons are very light, then in principle from their decays, you should, they will go through dark shower. And they produce many hidden hadrons. Then they decay back to standard model. These dark shower jets will probably look different from the standard model jets. But in order to distinguish them, one may need some detailed information of these track patterns. This is a more detailed study. Maybe machine learning will help later on. So let's discuss the collider search and the constraint on this type of scenario. Now first, at LHC, now we find that the light hidden fermions are dominantly produced through the Z production, Z pole, because we just produce many more Z's than Higgs. Now the typical number is for m equal to TeV and 13, we synthesize a 13 TeV, we expect the cross-section to this light fermion to be ordered a picobar. Now, if lambda is big, so the dominant decays into two hidden mesons, then there are a few interesting search channels which will be discussed. But if lambda is small, things will become more difficult. If lambda is small, first you may, instead of going to two hidden mesons, go to more, like 3, 5, and so on. In this case, then they just decay back. Then all the final decay products are very soft because you only have 90, say Z is 90 GeV divided into 10 or some particles, and then each of the molecule is very soft, so it will be hard to pass the cut. For even smaller lambda, then they decay end up with 2 jets. Now again, this has large standard model background. So these 2 cases, for small lambda, it will be very challenging at the LHC. But if we have some future lepton collider which can produce large number of these, then they will be very good to search for this scenario. So let's go back to the case for large lambda, so the decay to 2 mesons to be dominant. First, we think the leading decay may be into a pseudo-scalar and a scalar. The scalar will decay to vector plus a pair of standard model fermions, but they are very soft, so one probably will be lost. So we can consider the case when eta decay into a pair of BB bar and the upsilon decay into a pair of leptons. And this is a promising channel. So similar final state has been used to search for Higgs decay to 2 pseudo-scalar into a BB mu. There's another search, and in fact, CMS search just appeared 2 days ago. Now they search for these Higgs. Now because they have a total invariant mass around the Higgs, this is their signal region. Our signal, in fact, will appear in their controlled region. Consider and because this Z is lighter, the thing we get is much softer. It's harder to pass their cut. So actually, the signal efficiency will be much smaller than the Higgs efficiency in their case. Is roughly 2%. Now in this case, we expect for some benchmark M2 TeV, we expect maybe 10 or less event, signal event, where the background is order 100. So right now, I think it's still safe for this benchmark, but it can be getting interesting when we have more data. Now the other maybe promising signal is more suppressed decay into upsilon and chi go back to upsilon. When you have 2 upsilon, you can get 4 leptons in this case. It's a clean signal. Certainly you have a lot of search for after the CMS for Z going to 4 leptons. Right now the number agrees with standard model, so we can put a bound on this channel. This F number is a fraction of the Z into these fermions end up with this particular final state. We expect to be, because suppressed, maybe less than 10%. Right now, the bound can give us this to be like 4.8. So there's still 1 or 2 order magnitude away. But when we have more data, this mode can also be interesting. Then one can also consider Higgs decays. This is because this is extensive research, but the current bounds, the best bound is around 10 to the minus 3 to 10 to the minus 4, but this is not yet sensitive to our expectation because our branching fraction into these light fermions is already 10 to the minus 4. This hasn't taken into account the further branching fraction into this particular final state. So, but then in the future, high luminosity LHC or Higgs factor may may probe some interesting regions. Now, then consider the other case when we have a very small lambda. In this case, the decay into hidden stack fermions will form jets. Now, they may look different from QCD jets, but it's hard to trigger on them directly because they are not very hard. One usually have to consider their production associated with a hard object. Now, and also for very small lambda, one can expect these hidden mesons can be long-lived. We can get actually displaced vertex from their decay. Therefore, in this case, we will get the emergent jet. In this case, there is emergent jet search at CMS, but this search doesn't apply to this case because they consider a different model where they use require very high PT for the total high PT for the signals. Where in our case, the PT are pretty low because they come from Z decays. So the potential reach of this case is being studied. Especially very expensive by Linfeng right now. And the other possible place to look for it is the HCB, because the HCB has a low trigger threshold and very good track and vertex reconstruction, and they can look for this softer emerging jet. It may be also a good place to look for these signals. Now, let me just consider another variant. Basically, so far we consider one flavor hidden QCD. One can ask what about if there are more than one flavors. This can also happen in our model if we just make a further modification. If we consider the two SU3 in the B and C sectors are actually identical, because each sector has one light flavor, then in this case we will have two light flavors. In this case, the lightest mesons will be the Susan-Lambo-Gosson-Botan. They will be dark ions. They are expected to be much lighter than the other mesons. So the signal will be dominated by these dark ions. Now, how does this dark ion decay? It depends on the model. In fact, if Z2 is exact, these dark ions carry iso spin. In fact, they can be stable. They can even be dark ions. But this is not. This will be a different talk. If the Z2 is broken, then this dark ion can decay back into the standard model. But it depends on how much this is decayed. And also dark ions are light. So typically, in this case, we expect long-lived dark ions. So we see displaced decays. So again, this is the case we will also expect emerging jets. So, okay, now let me conclude. We just, the light composite state from hidden gauge group can be very generic in hidden valley type models. Now include many neutral naturalness models. Now their coupling to Z and H can be induced through mixing with the heavy states, which carry both the electroweak and standard model electroweak charge and hidden gauge group charge. Now, in this case, then they can be produced in real Z and Higgs decays. Now, most of these exotic Z or Higgs decay studies right now are based on some simplified model with some elementary new state, maybe putting a dark photon and so on. Now here in this model, there are some relations. For example, when they are bounced from some composite sector, we expect a few of them with certain mass relations. Also, the coupling to Z and H determine both their rate and also how they decay back into the standard model. So doesn't have a lot of parameters, basically controlled by two parameters, the capital M and the lambda. So it provides a good new possibility for these searches. And in particular, we have seen a future high luminosity lepton collider will be very useful in searching for some of the cases we consider here. So that's for your time.
you have like neutral dark matter candidate in your model?
Well, in that particular model, of course, it's supersymmetric expansion. It has the standard neutrino dark matter, but it can have different type of dark matter. As I just earlier said, if in this particular variant, if we consider the Z2 is exact, that is isospin is exact, then these dark ions can be dark matter. In fact, they are the so-called Hsin dark matter, the strongly impacting massive particle dark matter people have discussed before. Of course, there are also additional, like the dark baryons. If there's some asymmetry, one can also get the contact from there.
I would just say that, you know, your emphasis in the searches was looking at high energy colliders.
Yeah.
But, you know, waiting for a future lepton collider seems like a really bad idea, especially today.
Yes.
At the same time, all these long-lived particle searches, you know, Phaser, Methuselah, Codex B, they're perfectly suited to looking for this. Because you have a state that's less than 5 GeV typically, right?
Yes, we could have. It depends on lambda. If the lambda is small, you get the states light.
You made some argument about the running should be similar to the QCD running.
Yes.
As long
But
as
we have, well, just in that particular model, typically we get the lambda bigger than 5 GeV, but you can obviously stick into more particle, making the running smaller, then it will be smaller.
okay.
It's more modern.
But as soon as that mass scale gets below 5 GeV, you can make these things with B decays. You know, those are the ways to go. There's far better experimental prospects for that sort of thing than for, you know, 100 million Z's or whatever.
Any further questions? Let's thank Hsin again for the wonderful talk.